Hello everyone. Imagine you are tasked with making a blue whale fly from the ocean into the sky without hurting a fin. In mass spectrometry, we face this daily, moving massive wet biomolecules into a vacuum. Today, we master the bio gateway. We move from operators to specialists who know exactly how to make molecular giants fly. For decades, we failed. We tried to blast them with heat, and they just shattered. John Fenn famously said he gave wings to molecular elephants. We are going to learn the physics of the Taylor cone and the drama of the Coulombic explosion. By the end, you'll see why this is the most elegant way to treat a molecule. Our briefing today covers 4 chapters. Sector A, the birth of the Taylor cone, where liquid dreams of being a gas. Sector B, Rayleigh limit, the point of dramatic tension. Sector C, soft ionization, the gentle touch. And Sector D, nano ESI, the elite laboratory strategy for sensitivity. Specialists' insight, the Taylor cone, is where chemistry meets high-stakes geometry. Look at your screen. Liquid flowing through a needle under 2 to 5 kilovolts. The liquid surface deforms, caught in a tug-of-war. This cone is the exact point where the whale first begins to leave the water. Why is your spray unstable when moving to 100% water? Water has very high surface tension. It requires a much stronger field to form that cone. A pro knows that if you don't adjust to distance or voltage, the whale never leaves the ocean. You need to compensate for the physics of the solvent. Once emitted, droplets shrink, but the charge stays on the surface. Imagine a crowded room where the walls are closing in, and everyone absolutely hates each other. That is the life of a primary droplet. This crowding leads us to a point of no return, the Rayleigh limit. This equation describes structural integrity. When charge repulsion overcomes surface tension, the droplet shatters. This is the moment where the liquid explodes into the gas phase. It's structural drama at its peak. We call this Coulomb fission, or a Coulombic explosion. The droplet doesn't just split, it bursts into smaller progeny droplets. This happens again and again, evaporation, tension, explosion, until we are left with nanodroplets. Why call it soft? Because during the chaos of explosions, the molecule barely changes. ESI is the peacekeeper of mass spec. It's a paradox. The most violent-sounding process, a Coulombic explosion, is the gentlest way to treat a molecule. If you want sensitivity, go small. Nano ESI droplets reach the Rayleigh limit faster because they are already 10x smaller. They require less work to become naked ions. This is high-level lab strategy for trace analysis. Don't be afraid to split your flow. A specialist knows that ESI cares about concentration. Lower flow leads to smaller, more efficient droplets. You are controlling the spray to measure the giant. Recap. 1. Taylor cone. Balance. 2. Rayleigh limit. Tension. 3. Coulombic fission. Liberation. 4. Soft ionization. Protection. You now understand that ESI is the bio gateway. Silence the doubt. Master the mist. You've mastered the gentle mist. But what if you need to detect a single atom of lead in a trillion parts of water? Join me in Module 6-2, the plasma torch, where we leave the mist and step into the 10,000-degree fire of ICP-MS. I'll see you in the heat.